Welcome back, ladies and gentlemen. In this video, we'll be looking at some examples of how to work with momentum and impulse. This will not include any work with collisions. However, we will kind of take an initial look at what we call recoil. So, to save a bit of time, I went high-tech with this. Here's our first question. How much force is needed to stop a child on a skateboard in 3 seconds if the child is moving at 2 meters per second? All right, so what we always do in physics is we draw a diagram. And we got the child, yay, and we have a velocity here of 2 meters per second. Okay, and we're going to stop that child by applying a force. So here's what we do. We know about the equation for impulse and momentum, and most traditionally this is how you'll see it written, but the child's mass is constant, the velocity is changing, we're going to apply a force. We have a certain period of time over which that force is applied. It's the force we're looking for, so isolate that, divide both sides by t. We have m delta v divided by t. And at this point, it's really easy with the information given. We can find this force that we need. So we have a mass of 40 kilograms. And we have a change in velocity. Okay, well, a change in velocity is a final minus initial. Our final is going to be 0, and our initial is going to be 2. So this is a negative 2.0 meters per second. And our time is 3 seconds. So force, looks like we're going to get a negative answer. Does that make sense? Well, yeah, it does. If we said, look, that according to this information I've got, the positive direction is off to the right. So there's our coordinate system right there. And so this force to stop the child has to be a force acting in the negative direction. There's our force, and that will produce that delta V, the negative delta V, to stop it. That makes a lot of sense. The acceleration will also be in that direction. And, well, good, that jives. That should take you way back to some pretty basic physics from first semester. And so here we go. So 2 times 40 is 80. 80 divided by 3. Do the math in your head. You get, what is that, roughly 26.7 newtons. There's the force needed to stop that child in 3 seconds. What if you wanted to stop the child in less time than that? Let's say you wanted to stop the child in 1 second. Would you need more or less force? Well, to stop the child faster, to produce the change in velocity more quickly, you would have to apply a larger force. It would be harder. So in 1 second, you would have 2 times that's 80, and that's divided by 1. So you'd have 80 newtons required, instead of the 26 or 27 roughly. So basic way to work with momentum, changing momentum, and impulse on this side, right? Cool. Let's look at another example. We're going to compare that to stopping a car. So our next question, here we go. So now we have a car. Diagram. High-tech car, right? It kind of looks like it's going to the right this time. So there's our initial velocity. And let's say this car is going at 2 meters per second. It's just crawling along real slow. Well, as soon as I draw or write this down, then there's something else you know. The coordinate system is now positive to the left. So keep that in mind, right? Same setup, same equation. First time. Delta V, and you want to stop this car, and you want to do this in 3 seconds. So m delta V divided by t, and plug some numbers in. We have 700 kilograms, and we have a delta V of negative 2 meters per second, and we have a time of 3 seconds. So when you do this math, 467 newtons. There's our force. Let me carry this down like that so we look complete. All right, so the child on the skateboard moving at 2 meters per second required roughly 27 newtons to stop in 3 seconds. The car moving at 2 meters per second required nearly 470 newtons to stop in 3 seconds. And when you do that comparison, 467 newtons divided by the 26.7, oh, by the way, I'm sorry, I missed a negative sign, aha, direction, because in this case the force is going to be going in that direction, which is our negative direction. And that makes sense, we want the acceleration to be in that direction also. When the acceleration and the velocity are opposite of each other, you will slow down that object. Okay, now back to this. Well, this ratio is greater than, let me do a greater than 17 times. So it's greater than 17. So the force required to stop this car is over 17 times larger than the force required to stop the child. And so why is that? Well, it's real simple, and I'm sure you see it. It's the mass. The mass of the car is so much greater than the mass of the child. That's it. That's the only difference here in this problem. And that's what makes it harder to stop. So working with this equation and dealing with change in momentum is relatively straightforward. And we'll see in a minute how this applies to rockets. We are going to get to rockets. But I want to look at one more example. And in this example, we're gonna first introduce this idea of recoil. Now, check this out. We have an astronaut on the ISS, that's International Space Station, and this astronaut throws a 1 kilogram bottle. I'm not going to draw the whole ISS, but check this out. We have a water bottle, not to scale. Okay, that's a terrible water bottle, but you get the idea. The water bottle is thrown this way, let's say, at 8 meters per second. Okay, so as soon as you see that, and given that that's a positive, we know our coordinate system, right? And so now, what's the deal? Well, there was a force applied to this water bottle to get it to fly this way at 8 meters per second. Newton's third law of motion says that forces always come in pairs. So the force, this arrow isn't the force, this arrow is a velocity. Let me label this. Velocity of the bottle. So let me use a different color for forces. There must have been a force applied to the bottle. And Newton's third law says, well, the forces always act in pairs. They always act on opposite or different objects, and they always act in opposite directions. There must be an equal force acting in the other direction and acting on a different object. The only other object it could be is the astronaut. So check this out. The astronaut pushes on the bottle pushes back on the astronaut. Aha! And the result is the water bottle has a velocity after the throw of 8 meters per second. What we want is to know the velocity of the astronaut in the other direction. The astronaut will have a velocity. The astronaut will recoil the other way. It's a weird thing to say it like that, right? We're not used to talking about the recoil of an astronaut. Guns have a recoil. Okay. But it's the same principle. If this were a bullet and this were a gun, the bullet goes that way. Well, the gun goes that way, right? Water bottle goes to the right. Astronaut must go to the left. And that is exactly what happens. Well, how does this work then? So what we know is this. During the throw, while the astronaut was applying a force to the water bottle was applying a force to the astronaut. And so what are those forces? Well, we have a force, and the forces are equal to each other, and we have a time of contact. The amount of time that the astronaut exerts a force on the water bottle is the same as the amount of time the bottle exerts a force on the astronaut. So force is the same for each one, and time is the same for each one. So we could say, well, the force on the astronaut and the time on the astronaut is equal to the force on the bottle times the time on the bottle. So the impulse applied to one will be equal to the impulse applied to the other, because time of contact is the same. We need to realize that. Okay. Well, from this, look, what impulse does is an impulse acting on something is going to change the object's momentum. So we can say, therefore, there's going to be a change in momentum of the astronaut, and it's going to be equal to the change in momentum, remember lowercase p is momentum, of the bottle. Well, that's pretty awesome. But within the change in momentum, we have a mass times a change in velocity of the astronaut. And over here we have a mass, I should say astronaut, mass of the astronaut, mass of the bottle, times change in velocity of the bottle. And this is where it gets interesting because we know that the masses are not the same. And therefore, the velocities or the changes in velocity will not be the same. So here's how we work this out. Now we have an equation where we can start plugging numbers in. We know the mass of the astronaut was 70 kilograms. We do not know the astronaut's change in velocity. Change in velocity astronaut. But over here, the mass of the bottle. Well, the bottle was a 1 kilogram bottle. And the change in velocity of the bottle. So this is interesting. Before the throw, the bottle would have been going 0, and now it's traveling at 8. So the change is a positive 8 meters per second. Okay, now, how do we figure this out? Well, this is pretty easy. All I got to do is do some multiplication and some division, and I'm going to see that the change in velocity of the astronaut is 1 kilogram times 8 meters per second divided by the 70 kilograms. Got to bring this over to the other side here, and I'll squeeze it in. Change in velocity of the astronaut. And once I do this math, what I get is 0.114 meters per second. So, I'll put this up over here. So, with this change in velocity, well, a change in velocity of the astronaut is a final minus an initial. And so the final velocity is really the thing we're looking for. So now I have my initial is 0, and I know my change, 4 meters per second, and my final velocity is what I want, and my initial velocity was 0, and so from that I can find the final velocity, or the resulting velocity of the astronaut, and I simply get this. Now this is kind of interesting that what I've got is, well, a positive velocity of the water bottle. I ended up with a positive velocity of the astronaut. And that can't be, because they're going opposite directions. So where did I go wrong? Where did I make my mistake? So look at this. I've decided that positive is to the right. So this velocity of 8 meters per second of the bottle is positive. Here's where I went wrong. Look at this force acting on the bottle. That's in the positive direction, right? So the force on the bottle is positive direction. Well, what about the force on the astronaut? That's in the negative direction. So I really need a minus sign here, and that puts a minus sign here, and that puts a minus sign here, and that does that. And when I find this, well, what I really want is to get rid of the minus sign on this side, so I have to put the minus sign here. And that means my minus sign carries over here and there. And now I'm correct. Now I have a positive velocity of the water bottle and a negative velocity of the astronaut. And that makes a lot more sense. So there's the final resulting velocity of our astronaut. Keep track of your coordinate system. It really does matter. Momentum is a vector like force and like velocity. The direction of the momentum and in direction of change momentum also matters. So the minus signs, they matter. You got to keep track of those bad boys. Okay, so next, what's the deal with rockets now? So we worked through a few examples, just general types of things. And well, okay, I want to consider a couple things. This will get to rockets. Here we go. You'll see. But in general, if we were to look at amount of force and amount of time that the force is applied, let's say we're going to graph the two. We're going to take force on the vertical axis and time on the horizontal axis here. Okay. Can force be negative? Well, yeah, I guess it can, but don't worry about that at the moment. Well, let's say you apply a constant force over a certain period of time, and then you just kind of stop applying that force. Okay. So the dotted line doesn't represent any amount of force. It's just marking a location here. So this is going to be, well, time 1, let's say, and this will be, let's say, force 1, a certain amount of force, right? So look at this. What do we have going on? We know we've been studying impulse, and impulse is force times time. So if we take this quantity here, which is the amount of force, and we take this quantity here, which is the amount of time, and we multiply. Well, you know what we're doing? We're finding the area underneath the line here. So this area. Aha. So impulse is also equal to the area under force time curve. Now I'm going to use the word curve even though that looks straight. So impulse on a force time graph. Impulse is the area under the graph. Okay, very straightforward, no big deal. And so we've done stuff like this before. When you saw this, this is similar to a position time graph, a PT graph, or similar to how PT graph relates to velocity time graph. So let's say you had a velocity for a certain period of time, right? Well, if you look at velocity times time, the area under a velocity time graph gets you displacement. Well, here, force time, and the area under the graph gets you impulse. Okay, well, the thing about impulse on a graph like this is, do another one, force and time. You could have a certain amount of impulse. Now, remember what impulse does. Impulse changes momentum of an object. You could apply a force like this, and call this force 1, and you apply it for, say, this amount of time. And let's call this time 1. You're going to achieve a certain amount of change in momentum because you have a certain amount of impulse that you're applying to that object, right? Could you achieve the same change in momentum using a different amount of force? Well, sure you could. What if you doubled the force? So you went to force 2. Well, and you apply that force consistently, then what you're going to need to do to get the same area underneath your curve, you're going to have to go to the half the time. So T2, to achieve an equal amount of impulse, then what you have now is let me use a different color here so that it kind of stands out. The area under that new curve is going to be equal to the area under the original curve here. It's just a different shape to it, but you get the same amount of area, and therefore you get the same amount of impulse. So you would have F1 times T1 equals F2 times T2. You get the same area underneath, you get the same impulse, and therefore you would achieve the same change in momentum using a different force. If I wanted to go smaller force than F1, I would need to go for a longer period of time to achieve the same change in momentum. So why bother looking at this? Well, the reason is, when you look at the performance of rocket engines, and you look at a force time curve of a rocket, typical model rocket, this is often how you'll see them represented. As soon as you ignite the engine, it's going to start blasting that hot exhaust out the back, and it achieves a pretty large thrust force pretty rapidly. But then as it continues to burn, that thrust force kind of tapers off a little bit and does something maybe like that. And this is interesting. You've got several things happening. First of all, you can clearly see there's an amount of time here, and you can clearly see there is a maximum amount of force generated So, what the heck's going on? So we have F max. That's like a maximum thrust generator, okay. And here you have the time of the thrust that's applied. So the amount of time of the burn. After that time, all the fuel is spent and no more thrust is generated. Well, okay, but there's something else here. We were dealing with these here, which were basically straight lines. And now we got this messy curve. Well, there is an average amount of force. And where does it exist? The average amount of force is, well, if you just took the average of all these values, if you were into the calculus, you could do stuff like that pretty easily. But we're going to just eyeball it and say, you know what, it might be about here. And so I'm going to do that, and I'm going to bring this down to the time. And the reason is this. I'm going to mark this as force average. And so this is cool because now I can say, look, okay, the reason I can say this is the average is it's almost like I can take this amount up here and use it to fill in this that's missing, and I get an equal amount. And the handy thing about, oh, by the way, little missing amount over here too. The handy thing about that is now the area of this rectangle is easy to compute, whereas the area under this changing curve is not so easy if you're not using any calculus. So we're going to look at the average force, the average thrust of the engine. And we're going to be able to say, well, look, that average times the time is going to get you an impulse. Well, it is an impulse, but it's going to produce a change in momentum of the rocket. And the rocket's momentum starts at 0 on the launch pad, and it's got some maximum value after all the thrust has been applied and all the fuel has been used up. And this is interesting because different engines of different classifications are going to have different types of shapes to this curve. You'll sometimes run into stuff like this. Oh, if I could find it. Here we go. So check this out. Here's a typical thrust curve of an engine put out by Estes, which is a company that makes model rockets and stuff. So you see the real fast spike in the amount of thrust produced. It tapers off, and you have an average level marked. And at some point, all the fuel is used up. And in this case, for this engine, the fuel looks like it's used up pretty quickly, less than a second. And then there's a delay charge or delay period where something inside the engine is burning, but there's no thrust being produced, no measurable thrust. And then some period of time later, after the fuel is used up, there's an ejection charge to cause the parachute to deploy and all kinds of good stuff. And you get your rocket back. So one last thing to check out is how we might look at these in simplistic terms. We have right here a certain force time graph, and we see that, you know, on this graph we only have this going on. So what's the area of that graph? Well, there's more than just the area that you want to pay attention to, but the area does matter, because you want to know the impulse, and the impulse measured in Newton seconds, because we have newtons and seconds in our units. The impulse can tell you the classification, or the other way around, the classification on the engine can tell you the typical impulse it will provide. So in this case, we have 5 times 1/2, so 2.5. So 2.5 puts this in the A engine category, right? Now an A what? So the average force was 5. And if you look at the codes on engines, the second letter is the average thrust in force measured in newtons. So in this picture we have a B62, but look at this. This we already know is an A engine by looking at the impulse, but the thrust is 5 newtons. So instead of just saying an A, we can say this is an A5. Now we don't know what comes next on the delay. We don't have any information about that. The final number is an amount of delay, and remember on this graph, this is the delay period. And on your engines, you're given that number on the engine, but here we don't have that. So what we do know, we have an A5 engine here. A from the area under the curve, we calculated that, and 5 from the average thrust. Well, this is going to be a 5 average thrust, but what's the area? The area is going to be 5 times 1 is 5. And so 5 Newton seconds of impulse gets us a B engine. This one is a B5 engine. What about this guy? Again, we have 5 newtons of thrust, but what is the area? We have 5 times 2 is 10, and 10 is going to give us a C engine. This is going to be a C5 engine, right? So that's what these types of graphs can give you. Now, there's another thing we can look at. We can look at an empty graph, and what if I say, you know what? What if I give you a very common, one of the most common types of engines, an A83. Now, the part that goes on the graph is just the A and the 8. We're not going to put the delay in there, although we could. I could show you that. So watch this. I know that the 8 is going to be the average thrust, and so I have to fit 8 in this scale. So what if I go 1, 2, 3, 4, 5? Nope, that's not going to work. If I go 2, 4, 6, 8, so there's 8. And it's an A engine. So an A, well, typically an A, let's say it's going to have, it could be anywhere in this range, but let's give it the 2.5. So we need the area to be 2.5. Well, what's this going to look like? 2.5. I need a time of 0.31 seconds or so. So I need about a third of a second, about here. It's going to be pretty skinny. And I have to draw that horizontal line solid because that is a measurement of force over time. This is a dotted line just marking a location. And so that's what the force time graph could look like in very simplistic terms. Force time graph of an A3 engine, right? A very powerful model rocket engine would be a D12. You could have a D12-3, a D12-5. So the 12 is the average thrust. And so I'm going to go 2, 4, 6, 8, 10. That's not going to work. 3, 6, 9, 12. So now that line becomes the 12. Okay. Now a D. Well, a D is going to give us an impulse of 10 to 20 Newton seconds. Let's go with the 20. So I need a time of 1.66 or roughly 1.7, 1 2/3 seconds right there. So dot, 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 all the way up, and there. And that is the thrust curve for a D12 engine. Now what about the 3? Let's check that out real quick. The 3 is a number of seconds. So from here, I have to go 3 seconds more, and then the delay charge will activate. Not delay charge, sorry, the ejection charge will activate after the delay. So 3 seconds from there. Well, there's going to be 1, there's going to be 2, there's going to be 3, about there. So that's my delay of 3 seconds. And then at this time, during this delay time, there is no thrust being produced. The rocket is coasting in the air. Probably still headed upward, but coasting. And then at this time, the ejection charge fires, poof, your parachute comes out, and you get your rocket back after a few more seconds as it descends. Okay, so that's a bunch of stuff with momentum, impulse, and also incorporating model rocket engine performance. Thanks for watching. I'll catch you next time.